Hello everyone. In today's video, we are going to solve a system of simultaneous equations by matrix inversion. In this particular question, by using matrix inversion, they have asked us to solve the following set of simultaneous linear equations. We need to find the value of x, y, and z. In order to solve the above system of simultaneous equations, we need to rewrite it in matrix form. Let us label the coefficient matrix by A, the variable vector by x, and the constant term vector by d. This is the matrix inversion formula to find the solution to the system of simultaneous equations. X is equal to the inverse of the coefficient matrix A times the constant term vector d. In order to find the inverse of a matrix, there are two conditions which must be satisfied. The first condition is that it should be a square matrix, and the second condition is that it should be a non-singular matrix. Evidently, the coefficient matrix A is a square matrix of 3 by 3 order. In order to satisfy the second condition, let us find the value of the determinant of the coefficient matrix. On deleting the row and the column, we are left with elements 4, 3, 1, 1. Next is element 2. Its positional sign is minus. On deleting the row and the column, we are left with elements 5, 3, 6, 1. Next is element 1. Its positional sign is plus. On deleting the row and the column, we are left with elements 5, 4, 6, 1. Let us solve it further. Since the value of the determinant is not equal to 0, hence it is a non-singular matrix. We can now proceed to find the cofactors of the coefficient matrix A. The element A11 is 3, its positional sign is plus. On deleting the row and the column, we are left with elements 4, 3, 1, 1. Next, element A12, its positional sign is minus. On deleting the row and the column, we are left with elements 5, 3, 6, 1. Element A13 is 1. Its positional sign is plus. On deleting the row and the column, we are left with elements 5, 4, 6, 1. Element A21 is 5. Its positional sign is minus. On deleting the row and the column, we are left with elements 2, 1, 1, 1. Element A22 is 4. Its positional sign is plus. On deleting the row and the column, we are left with elements 3, 1, 6, 1. Element A23 is 3. Its positional sign is minus. On deleting the row and the column, we are left with elements 3, 2, 6, 1. Element A31 is 6. Its positional sign is plus. On deleting the row and the column, we are left with elements 2, 1, 4, 3. Now cofactor of element A32, which is 1. What about its positional sign? Positional sign is minus. On deleting its row and column, we are left with elements 3, 5, 1, 3. So finally, for the last element, cofactor of element A33, that is element 1. Its positional sign is plus. On deleting its row and column, we are left with elements 3, 2, 5, 4. Let us now frame the cofactor matrix. The cofactor matrix is a matrix which comprises of all the cofactors of each element of a matrix. The cofactor of the element A11 is 1. The cofactor of the element A12 is 13. The cofactor of the element A13 is minus 19. The cofactor of the element A21 is minus 1. The cofactor of the element A22 is minus 3. The cofactor of the element A23 is 9. The cofactor of the element A31 is 2. The cofactor of the element A32 is minus 4. And finally, the cofactor of the element A33 is 2. Let us now frame the adjoint matrix. The adjoint matrix is nothing but the transpose of the cofactor matrix. The transpose of a matrix is obtained by interchanging the rows into columns or columns into rows. Let us rewrite the first row as first column, the second row as second column, and the third row as third column. Now we are going to substitute the value of the determinant of matrix A and the adjoint of matrix A in the formula of inverse of matrix A. The value of the determinant is 10. This is the adjoint matrix. Let us substitute the inverse of matrix A and the constant term vector D in the matrix inversion formula. Let us multiply the first matrix with the second matrix. Let us multiply the first row with the column vector, the second row with the column vector, and the third row with the column vector. Let us simplify it further. Let us now multiply the constant 1 by 10 with each element inside the vector. These are the values of x, y, and z. Therefore, the solution to the system of simultaneous equations are x equals 1, y equals 1, and z equals minus 2.